Hey guys. Anyone in the stream? Hello? There's one person live right now. Hello. And we just had another person join. And another person. Okay, cool. That's 3. I'm going to wait another 30 seconds, and then we'll start. How's everyone's week been? Yeah, same. I'm kind of already in the fall break mood, so I'm not really paying much attention to my classes. So yeah, I'm tired too. Anything in particular, or just tired? Yeah, English work can be tough. It can get very tough because a lot of teachers like to give busy work instead of actual real work, but that's not my job. Ow. Ow. That sucks. I'm really sorry about that. I'd say hopefully this stream is a little less tiring when you procrastinated. Yeah, that still sucks though. But hopefully, I'd say that this stuff, hopefully it's a little more relaxing for you. But this kind of stuff doesn't click immediately for chem students. So we'll start. So follow Fiveable on social media for all the alerts about the streams. To me, it seems like chemistry is ahead right now a little bit with chem curriculums. So getting alerts if you get more ahead, or there's some subjects I guarantee that are a little behind just by pure statistical nature. So you can watch those streams and review on the stuff that you learned in class before. You can watch these streams and get ahead in your classes, which will make learning in class a lot easier. But of course, you have to get alerted for the streams. So if you get alerted, then you'll be able to get ahead in your classes. And chem is especially an important class to get ahead in. So we're going to be reviewing polarity in molecules and then talking about dipole-dipole forces between polar molecules. We'll talk about hydrogen bonding, which is just a special case of dipole-dipole forces, London dispersion forces, which are the forces between every molecule, all these forces' relations to physical properties, and then we're going to be talking about some examples of IMFs in biomolecules, like DNA and hemoglobin and all that good stuff. Wish that another person joined. Hey, Matthew. Okay, so to start, we're going to be reviewing polar molecules. So polarity is based off the idea of electronegativity, which is the tendency for an atom in a molecule to pull in electrons from the bond. So hydroxide right here, for example, there should be a negative charge in there more correctly, but it doesn't really matter. The electronegativity trend is the closer to fluoride it is, the more electronegative. With the exception of the noble gases, which don't have a defined electronegativity because they're not reactive generally. Of course, there's some exceptions, but we're talking about general trends here. And the bond is just a shared pair of valence electrons, right? But there's an uneven distance from the central atom and those that bonding pair of electrons in polar atoms, or atoms with an electronegativity difference, or molecules with an electronegativity difference. So when we're talking about hydroxide here, oxygen has a greater electronegativity. You don't have to memorize the values, but you can clearly see on the table, oxygen is much closer to fluoride than hydrogen is, so it has a higher electronegativity just by the general trend. So the electrons in the bond will be more hogged by the oxygen rather than the hydrogen. So there's an electronegativity difference there. And polarity is based off the whole idea that a big electronegativity difference means the molecule is overall polar, or rather the bond is more polar. And polar means this implies that the molecule has poles. For example, like a north pole and a south pole. Those are just they're two similar things on opposite ends, so we call those poles. In this case, the poles mean charge. So that bond in hydroxide has polarity, and that polarity is pushing towards the right. Because there's charges on both the oxygen and the hydrogen, so there's charge poles on each side, so it's a polar bond. And an even pole of electrons is called a dipole moment. Dipole meaning two poles, and a moment in general is just a product between a distance and another quantity. So in this case, a dipole moment is the product of the separated charge in the distance. You can have really any moment. You can have like a force moment, like if you're pushing on a door. The further away you push from the door from its hinge, the easier it's going to be to push the door. So the greater the moment, the easier it is to push the door. And in the same case here, the dipole moment is just that quantity that's facing towards the right. Like if you're traveling down a highway and you're talking about you want to encode which direction and how fast you're going, that'd be something called a vector quantity. In the same case, the dipole moment, which is that Greek letter mu, looks sort of like a funny U. That's a vector quantity in the molecule, and that bond is polar. So because electrons are pulled and pushed, they create positive and negative charges. More formally, as a partial positive charge. For example, in hydroxide, the electrons are moving or are pulled toward or further towards the oxygen. So because electrons are negatively charged, there's going to be a higher negative charge centered around the oxygen atom in the hydroxide molecule. And conversely, because of conservation of charge, if one thing goes up, the other has to go down, and if one thing goes down, the other has to go up. So there becomes a partial positive charge on the hydrogen, just by the consequence of the dipole moment. So when we're talking about bonds being polar, just because a molecule has polar bonds doesn't mean its molecule is polar, right? So if we have C2O right here, there's an issue here because both the CO double bonds are going to be polar. However, it's a vector quantity, so you have to include directions when you're adding them. And because the shape of the molecule itself is linear because there's no lone pairs in that oxygen. So the dipole moments are pointing in exact opposite directions, and they're the same magnitude. So their electronegativity contributions are the same. So when you're adding up those dipoles, you add up one, and then when you're adding it, you're adding a negative because it's pointing in the opposite direction. So total dipole moment is 0. So just because the molecule has polar bonds doesn't mean the entire molecule is polar. Like in this case here, like if you were traveling down the highway if you're traveling like down a town road, you're going 10 miles per hour and you're in the back seat, you throw a baseball back at 10 miles per hour, the baseball is going to stay still after you throw it out of the car, because although the speeds were equal, the throwing was in opposite directions. So they canceled each other out. The same case here. The dipole moments are equal, however, they're in opposite directions. So there's no net dipole, so the molecule is nonpolar. So that was a brief overview of polar molecules. I went kind of fast. I can go back to the slides again and explain things a little more in detail and a little slower. Just give me the word in the chat if you need a more in-depth briefing, because this is going to be really important. Matthew's good. Anyone else? Need some extra explaining? Okay, I'll give you about 15 seconds to speak up for anyone else that needs some more explaining. Okay, so this is going to be a really important idea, so you better understand polarity. If you don't, then you'll definitely get it by the end of the stream. So we're going to be talking about dipole-dipole forces. And And dipole-dipole forces are the electrostatic attraction between two polar molecules. And for example, we see hydrochloric acid here, or I'm assuming it's aqueous, but it's almost definitely going to be aqueous. So I'm going to build this molecule real quick with my modeling kit that I have here. So right here I have this red is Cl, this white is hydrogen. So right now on the screen I have something that looks like this, right? So these molecules will clearly attract each other, right? Because there's a negative charge next to a positive charge, and opposites attract. However, what would the case be if these molecules were perfectly like this, with the chlorines perfectly facing each other? They would very clearly repel. However, in terms of like temperature is just random thermal motion, right? Like if we're thinking about the atmosphere, the reason why the atmosphere has a temperature at all is because there's constantly molecules zipping around everywhere. And if there's two things like this is a very unstable state. So if a molecule like hits this hydrogen and doinks it, this will start repelling and this will start attracting. So the molecule will rotate and then they'll attract each other again. So you can think like if there's a sample of polar molecules, like you have a sample of hydrochloric acid, you can think that like, yeah, in some cases the two molecules will repel each other. However, there's a discrepancy because there's going to be random motion, or not random motion, but there's going to be motion that's caused by collisions that you can't really keep track of, at least accurately. And those molecules will rotate around and conversely attract each other. So when we're thinking about this molecule, if there's a chlorine right here, if it's just hit off its axis a little bit, this will repel at the same time of this attracting, so it'll rotate. Does that make sense? Macroscopically, yeah. Like if you have like a full sample of these, they'll be neutral. And the goal here is definitely to achieve neutrality, because neutral or charge neutrality is like the most stable state for a molecule to be in. So yeah, I mean, I guess in a sense, like the molecules wouldn't become neutral themselves because the molecules would still be very discretely separated. So the molecules would still be polar, but however, like in an effective sense, they would become neutral because it's just a negative charge next to a positive charge and a positive charge next to a negative charge. Yeah. So I'm going to show you a really scary drawing real quick for dipole-dipole forces in a more complicated molecule. This is called bromocyclohexane. And you may think that this is like a really weird way to represent a molecule. So if you look at the molecule in the bottom right, you see this sort of like zigzag structure. And this is essentially just a bunch of carbons that are bonded in a ring together. And when you flip it on its side, this is kind of what it looks like. Right? You have the head right here and the tail right here. Does everyone see that? That's sort of similar in structure? I'm omitting the rest of the carbons in the ring because they're not really relevant to the demonstration. But does everyone see the similarity in the drawings right there? Looking at the bottom right molecule. Okay, awesome. So if we think of something like this, right? There's a hydrogen on the back right here. Like in this page right here, I'm omitting the rest of the hydrogens on this carbon because again they're not relevant to the demonstration. But there's a polar bond between carbon and bromide. They're very far away from each other in the periodic table, so there's a polar bond there that's pointing towards the bromide. So if we have another molecule right here, which I can maybe muster up a thing real quick. Yeah, I can definitely build this up real quick. So take a bit. Okay, we are almost done. Okay, so I have the molecule, the second one right here. So these are the same. These are essentially the same molecule, right? But if these, like for the same rotational reason before, the carbon right here, because the carbon is the one that becomes partially positive, it'll attract like this to the bromide that's now partially negative. in the same reason for before, and the system will eventually come to this structure just naturally because of the rotation that we were talking about earlier. So even in more complicated molecules, even though there's like more than just one axis they rotate around, they're going to end up attracting each other in a similar fashion. So in here, I have the drawing that looks more like this, and they'll attract each other like that. Does that make sense? So this applies, basically the whole idea is this applies to like very big molecules because this is a very complicated molecule. Awesome. So we're going to go over practice, and the practice is, will a sample of hydrogen sulfide have dipole-dipole interactions? So the first step here is to think about the structure of hydrogen sulfide. If you can't really think about it, you don't know it, draw it out by counting the electrons. What do you guys think? Do you guys think a sample of hydrogen sulfide will have dipole-dipole interactions? Yeah, right. So when we were looking at the case of the C2O last time, the molecule was linear, so there wasn't any polarity, even though the bonds themselves are polar because the dipoles canceled out. However, hydrogen sulfide, there's two lone pairs on that central sulfide, so the molecule becomes sort of bent like this. So when it becomes bent, those dipole moments are not pointing in opposite directions anymore. They're pointing like this. So the total dipole moment, what you do when you like add those arrows is you go tip to tail, tip to tail. So when you have two dipoles like this, one goes like this, one goes like this, and the net dipole is pointing upwards like this. So the net dipole would be pointing through the sulfide. So it would be polar, and any polar sample polar molecules is going to have dipole-dipole interactions. How about carbon dioxide? Good, yeah. For the same reason that I was talking about before, the carbon-oxygen bonds will be polar, but the carbon dioxide molecule itself is linear. So those dipole moments will be facing in opposite directions. How about chloroethane, which is just C2H5Cl? You might need to draw that out. Anyone want to throw a guess out there? Okay, I appreciate you throwing the guess out, but yes, there is there are dipole-dipole interactions, and I can actually build out the molecule to show it. So if we have, this will be much easier if I use this one. So chloroethane is going to look, still building it out. Almost done. So this is what chloroethane is going to look like. You have two carbons, three hydrogens, two hydrogens, and then a chloride. And the CCl bond is polar, and there's nothing to cancel out this dipole moment right here. So that's why it would be polar, so it would have dipole-dipole interactions. A sample of it would. Does that make sense? Awesome, cool. So I have a challenge, and the challenge is samples of which molecule will have stronger dipole-dipole interactions. The left molecule is called 2-chloro-1-propene, and the right molecule is called 1-chloro-1-propene. Which molecule do you guys think will have stronger dipole-dipole interactions? You can throw a guess out there. Just call out left or right. And don't worry, I will explain the answer. Anyone? Anyone want to throw a brave guess out there? Appreciate the guess. No, it's the one on the right. And the reason why is because when we're talking about the molecule, I'll put it out again. So we have a double carbon bond right here. And then a hydrogen bond right here. So this is the one on the right. So if it attracts another one of these molecules, there's not going to be a lot of crowding around this molecule right here, right? So if we have another molecule coming in on this end, because this is going to be the carbon that's going to be partially positive, so it's going to be the one that is attracting this chloride and with other molecules in the solution. So when we switch them around, which is what the structure on the left is, do you see that there would be more crowding whenever the carbon comes in to attract with the chlorine than the previous case? Does everyone see that there would be more crowding on this one? Yeah, that's my bad. I totally should have talked about crowding. Crowding would be like there's a lot of other molecules that are in the vicinity that will hinder the ability to create those electric attractions. So, like for example, if I have an electron here and a proton here, there's going to be strong attraction. But if you put an electron in the middle, there's crowding right there. The electron can't get to the proton because there's that electron in the way. So it's literally just a mechanical crowding. So when we look at this molecule, more like this actually, this is the one on the left. There's a lot of crowding here between the. I'll build another molecule actually. That would probably make it a lot easier to visualize. Another one of these 1-chloro-1-propenes. That'd probably make it a lot easier to look at. I'm going to not include the hydrogens just because they're not really relevant. I'll keep the hydrogens on. So when these two molecules attract, the only place where this where this chlorine can like have an electrostatic attraction with this carbon is through here or through here, right? Because it can't come in through the top, because when it comes in through the top, this carbon is going to be swinging around and hitting this hydrogen, and with the same case here, it's going to be hitting this hydrogen. However, when we have the chlorine on the end, there's a lot of places. There's 1, 2, and then there's this configuration, which would be very attractive. So there's more degrees of freedom for that second molecule to come in, so it would have stronger dipole-dipole interactions. Does that make sense? Awesome, cool. So we're going to go to the drawing board, and we're going to talk a little bit about dipole-dipole interactions in hydrogen sulfide and chloroethane. We're going to draw interactions between the 1-chloro, or I don't need to draw those out, I just explained those. Draw interactions between 1-chloropropionene and 2-chloro-1-propene. So we're going to go to my neat little image editing software application window. All right, cool. So when we're looking at this hydrogen sulfide right here, which is what I was talking about earlier, when we're creating dipole moments, or we're drawing dipole moments, we have one dipole moment that goes like this and one dipole moment that goes like that. And this creates a partial positive charge on both the hydrogens. And this creates a partial negative charge on this. One thing I forgot to mention is that curly, funky-looking letter. That's a Greek letter, delta. Delta usually means a small number. So that delta subscript plus means small positive charge, and in the same case here. More accurately, you would have a 2 in front right here, because this sulfide has a -2 charge, but that doesn't matter for the demonstration. So when we're talking about the overall dipole moment in the molecule, we simply just add the arrows. So when we're adding that and that, what we come up with is we add the arrows tip to tail, and what we end up getting is a dipole moment that goes right through the center of the molecule. Does that make sense? Awesome, cool. So we're gonna move on to this chloroethane. So I drew a little different like structure representation here. What you'll normally see this as is CCH, H, 2 more hydrogens, and then a chlorine right here. So I drew it like this because this is more accurate with the actual geometry of the molecule. So if you see the colored in wedge right here, that means the hydrogen is coming out at you, out of the page, and the dash wedge means just going backwards. So when we actually draw out, or we actually build the molecule, sorry if that made a loud noise. When we actually build out the molecule, I'm looking at the one on the right side, and ignoring the hydrogens on this molecule or on this carbon. When we're talking about this, do you guys see that it doesn't look like the bottom one? It looks like the top one, where you have one hydrogen coming out of the page and one hydrogen coming into the page. Does that make sense? So it's more like that or something like that. Yeah. So that's essentially what this molecular representation is, and it also allows you to look at the geometry of the molecule better. Because this is not like the molecule is not all in one plane, but this right here is unfortunately what you'll see on the AP test. So yeah, you'll just kind of have to visualize this stuff in 3 dimensions with this awful in the plane drawing. So when we're talking about the dipole moment here, the dipole moment goes out like that, creates a partial positive on the carbon, and then a partial negative on this chlorine. And then the chlorine from another molecule will come in and create an attraction with this carbon. Does that make sense? Awesome. And these are essentially the drawing again, the 2 things from the last slide. These are both the organic chemistry representations of the molecule. They're a lot simpler. But yeah, I mean, it's the same case here. If the carbon from one molecule attracts with this chlorine, there's going to be a lot of crowding with other atoms on the molecule. But for the same sake of the problem, there's a dipole moment, partial negative, partial positive, and in this case, partial negative, partial positive. And we're going to be talking about this molecular representation later in the stream, because like if we had like for example, if there was a chlorine, hold on, let me think about this. No, it's a bad example. I was going to say if there's a chlorine right here, it would look nonpolar, but it would be nonpolar anyways. So yeah, I mean, all you have to do for this kind of problems is like determine if there's like dipole forces between molecules and a sample. You just have to look if they're polar or not. But you look at their polarity by drawing up the structure. When you have a big structure like the chloroethane in the top right, I strongly recommend drawing it out as the geometry actually is. If you haven't done molecular geometry in your class yet, it'll be a little hard to do that. But essentially, those are tetrahedral and not in the same plane like the normal representation. Any questions about any of this before I move on back to the slides? Okay, cool. Back to the slides. So, hydrogen bonding. So hydrogen bonding is just the special case of dipole-dipole interactions where there's a hydrogen involved with another atom. And this is the strongest case because hydrogen has a low electronegativity. So for example, the HF bond has an electronegativity difference of 1.9. The HO bond has an electronegativity difference of 1.4, and the HN bond has an electronegativity of 0.9. So basically, a hydrogen bond exists when there's when in one molecule the hydrogen is bonded to either fluorine, an oxygen, or a nitrogen, and the fluorine, oxygen, or nitrogen in another molecule by it or adjacent to it has attraction with said hydrogen. So we're going to go back to the drawing board to talk about this stuff. Because I believe it's really revealing to talk about this through other things. So when we're talking about here's a great example for this, by the way. So we're going to talk about the water first. So there are polar bonds between these hydrogens and these oxygens. However, if you have another water molecule adjacent, I'm going to leave out the lone pairs in this one. This oxygen becomes very partially negative, and because the electronegativity difference is so high. And conversely, this hydrogen becomes a very strong partial positive charge. So you have a very strong partially negative charge on this oxygen. I'm going to label it with a star for very strong. And conversely, on this hydrogen, you have a very strong partial positive charge. So there's a very, very, very relatively strong attraction between this hydrogen and this oxygen right here. So that's why water has a high boiling point, because those molecules are very attracted to each other because of those big electronegativity differences. And that's all hydrogen bonding is, a special case of dipole-dipole interactions. So when we're talking about this molecule right here, I think this is methanol, which if you knew it was methanol before, I'm kind of worried for you because you're only in high school. So if we have another molecule here, there's going to be an H, an O, another C, and then a dot, 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 the rest of the structure. Again, there's a dipole moment this way, and there's a dipole moment this way. So this hydrogen and this oxygen have a very strong attraction between each other. So here's where the structure drawing thing comes in play. So when we have this nitrogen here, this is ammonia, normally with a positive charge right here, I think. Yeah. Or whatever, we'll leave it out. When you have ammonia, normally how ammonia is going to be drawn is like this. And when you draw out the dipoles in this way, this is how they'll look. So do you guys see how drawing it out like this makes it look like the molecule's nonpolar? All those dipole moments look like they cancel out. Does that make sense, guys? Like that's what that looks like. That's what you'd expect. Yeah. So like when we add these arrows, you get an arrow like that, an arrow like that, and then there's another arrow downward right here, and you begin where you started. So it cancels out to 0. However, that's not at all what the molecule looks like. The molecule actually looks like this, where you have here, I'll do it this way. This is what the molecule actually looks like. It looks like this. There's a geometry here that kind of planar drawing ignores. There is a dipole moment here because you have one dipole moment going this way, one coming this way, and one coming that way. So the net dipole moment points to the right, even though in that planar drawing it looks like it's nonpolar. So that's the kind of problematic thing here, and it does like because there's a lone pair on the nitrogen. There's kind of a problematic thing there that you like really, when you look at these structures, you really need to be careful how you're drawing them out because this molecule is definitely polar, and there is hydrogen bonding in them. So when we're looking at this molecule right here, and we have another NH3 coming in, this NH3 is going to be partially negative, I think. But But regardless, there's going to be a charge separation there, so it's going to create a very strong dipole. And because it's a nitrogen-hydrogen bond, it's a very strong electronegativity difference. So there's a very strong bond there. So essentially, hydrogen bonding occurs when there's one molecule that has a nitrogen or a hydrogen bonded to a nitrogen, fluorine, or oxygen, and then conversely, that hydrogen can be attracted to some oxygen on a molecule, some fluorine on a molecule, or some nitrogen on a molecule. Does that make sense? Okay, awesome. So London dispersion forces are next, and these forces exist in literally every molecular sample. However, hydrogen bonding forces are much stronger than dipole forces, which are much stronger than London dispersion forces. So really, the only force that's going to matter is the strongest force in the sample. Hydrogen bonding is going to be proportional or inversely proportional to the distance squared, I think. And then dipole is going to be inversely proportional to the distance cubed, and then London dispersion forces is going to be inversely proportional to the distance to the sixth. So if you think of what a graph of 1x or 1 over x to the sixth looks like, it goes to 0 very, very quickly, or it goes to a very small quantity very, very quickly. So those London dispersion forces become negligible as the distance grows. So the prominent force in a molecular sample is hydrogen bonding. If the criteria for hydrogen bonding is met, the criteria for hydrogen bonding means that there's a bond in the molecule between a hydrogen with a nitrogen, a fluorine, or an oxygen, and then an adjacent molecule has a fluorine, nitrogen, or oxygen near it. It's dipole-dipole interactions. If there are polar interactions that don't fit the hydrogen bonding criteria, and they're London dispersion forces otherwise. So London dispersion forces exist in all molecular samples. Dipole-dipole forces exist in a polar sample, and hydrogen bonding exists in a polar sample if and only if one of the polar bonds in the molecule is an H and an F, an H and an N, or an H and an O. So is that easy for everyone to understand? We'll go over some examples later because this kind of stuff is hard to look at without visualizing it. But yeah, okay. So we're going to do some practice. What kind of force is most prominent in the following molecules? So you guys go ahead and answer for hydrogen cyanide, HCN. What do you guys think? Will it be hydrogen bonding, dipole-dipole, or LDFs? In hydrogen cyanide, what do you guys think? Yeah, it's dipole-dipole. So there is a nitrogen in the compound. So the first the most knee-jerk guess would be hydrogen bonding. However, if we draw out the structure, the nitrogen is not bonded to the hydrogen, so that electronegativity difference is not going to play a role in there. How about ethylene glycol, which is that molecule with two of them, the CH2OH, and all that twice. What's the strongest kind of force in that one? What do you guys think? No, it's hydrogen bonding. Yeah, it's hydrogen bond. So generally, when you see these organic molecular condensed formulas, normally you think let's condense the H or put all the H's in one place. So the typical chemistry thing or Chem 1 thing to be or high school chem thing to do would be make that CH3OH instead of CH2OH, right? But the H not being with the carbon in the condensed formula means something. It means the hydrogen is bonded to the oxygen to make an alcohol group. So there is a hydrogen bonded to an oxygen. So there is hydrogen bonding. How about isobutene, C4H8? What's the strongest kind of force between those molecules? What Would it be hydrogen bonding, dipole-dipole forces, or London dispersion forces? No. So there's no nitrogen, there's no fluorine, and there's no oxygen in there. So there definitely can't be hydrogen bonding because that hydrogen would not bond to one of those molecules. For there to be hydrogen bonding, there would have to be a hydrogen bonded in the molecule to a nitrogen, fluorine, or oxygen, but there's none of that in the molecule, so it can't be hydrogen bonds. It's LDS. The molecule is nonpolar. It's very symmetric. So it's LDS because LDS exists in every molecule. The challenge I have for you guys is hemoglobin. You should be able to throw a logical guess out there, but yeah, no, there's no way you'll be able to draw that structure. But what do you guys think the strongest LDF or the strongest? It's not LDF. I didn't give that answer away. What do you guys think the strongest force in hemoglobin is? Yeah, it's hydrogen bonds. Yeah, you can't really definitively say that there is a hydrogen bonded to a nitrogen in that molecule, but you can definitely guess just by the sheer quantity of them because that's a lot of hydrogen and that's a lot of nitrogen. So to the drawing board. And we're going to explain these molecules a little more in depth and talk about their bonds. So this is hydrogen cyanide. I already have this stuff drawn out. So the CH bond is not polar. That's a big thing with these carbon-containing molecules. That CH bond is not polar. However, that CN bond is polar. So it points to the right for the same case here. And this is ethylene glycol, and this is the great example here. So if you're looking at it in this planar representation, you have two dipole moments. You have one going this way, and you have one going this way. However, with this planar representation, it looks like the molecule is nonpolar. But if you draw it out how the geometry actually is, it's very clearly polar. Do you guys see that in the bottom left? Yeah, okay, cool. So the top right is isobutene. There are no polar bonds in isobutene. This is C4H8. There's no polar bonds here. Every bond is a CH, so the strongest intermolecular force is LDFs. And this is not necessarily hemoglobin. This is a molecule that makes up hemoglobin. Hemoglobin is typically four different types of heme molecules that are bonded together via intermolecular forces. So what this structure means is if you see an elbow that's not labeled, that elbow that's not labeled is a carbon. And if that elbow also has remaining bonds left, for example, if we look at this elbow right here, there's 1, 2, 3 bonds, but carbon can hold another bond. So there's also another hydrogen coming off here. The hydrogen is just emitted because they don't really matter. So if we look at places where we can find hydrogen bonding, it's right here. It's right here. And is it anywhere else? No. So that's where hydrogen bonding can occur, is those OHs. These are truncated. It would look more like OH and OH. And then these are all polar because we're talking about the OH bond, like this entire string. So that's why hemoglobin can form hydrogen bonds. Does that make sense, guys? Yeah, anything with an alcohol can form hydrogen bonds. Yeah. Yeah, you're right about that. Good drawing there. Yeah. Okay, cool. So back to the slides. So we're going to talk about some physical properties of this stuff. So viscosity. I'm sure you guys have a vague idea of what viscosity is. It's how much a fluid holds together. So for example, maple syrup, or like what really viscous thing am I trying to come up with right now? I can't remember the word. That's unfortunate. Yeah, honey too. That's not what I was thinking, but yeah, honey, maple syrup, Molasses. That's what I'm thinking of. Yeah, molasses. They're all very viscous fluids, and I'm sure you can sort of infer that like these are very viscous because there's very strong intermolecular forces in between them. So the molecules being held together very quickly. So when you're trying to traverse through the fluids, I'm sure none of you have ever tried to swim in honey before, but if you're trying to traverse through the fluids, it's really hard because those intermolecular forces are holding the thing together very tightly. And surface tension. So I'm sure you guys have seen like videos of people like jumping off cliffs into water, and if you land on your belly, you're screwed, right? Even though we typically think of water as like a pretty like fluid, surface tension of water is very high because of hydrogen bonds. So if you land on water incorrectly, you're facing a lot of surface tension, and it's a lot of force on your stomach. So that's why belly flopping hurts. But yeah, so surface tension and viscosity, they're both sort of proportional to the strength of the forces. So melting and boiling point are also, if the IMF is stronger, if the IMFs are stronger in a sample, the melting point and the boiling point are higher. I hope that's intuitive. Viscosity, same thing, stronger IMFs, more viscous. And surface tension, stronger IMFs, more tension. So I'm going to practice. Can someone just give a brief explanation on why mosquitoes can stand on water but not liquid 1-octene? Why can mosquitoes stand on water but not that liquid substance? What do you guys think? Come on. No, not density. Yeah, there's strong IMS in the water that occur from the hydrogen bonds. So the surface tension is greater in the water, so the mosquito can stand on it. I don't know if mosquitoes can actually. Yeah. There's no hydrogen bonds in liquid 1-octene. There's only in liquid 1-octene there are solely London dispersion forces. So those are the weakest kind of intermolecular force. I'm not sure if mosquitoes are unable to stand on liquid 1-octene, but I imagine because that's a very weak fluid. So who in here likes biology? Or I can ask a better question. Who in here doesn't like biology? Is that a me to you liking it or you not liking it? Yeah. Okay. So sadly for you, this kind of stuff is very applicable in biology. And on the AP exam, you'll typically see these big biological molecules, and you'll be asked to identify the kind of forces between them. I remember on a practice exam I took last year, there was 2, I think, DNA molecules, and we had to determine which representation was correct based on the hydrogen bonds. So that was fun. Not. So the first thing is DNA. So the things I'll define are polymers and monomers. So if we think of like this is a monomer. Mono means one, single. But if we have like multiple carbons that are attached to this thing, it's multiple monomers being attached to make a polymer, a multiple. So DNA it's a polymer made up of monomer units composed of cytosine, guanine, adenine, and thymine. So I have the diagram right here. We have adenine and thymine on the right, and then guanine and cytosine on the right. And do you guys see how those two monomers are paired with hydrogen bonds? Yeah. So in terms of like I'm sure you guys all know the structure of DNA. It's like a double helix. On each sides of those helixes, those are base pairs that are just stacked on top of each other. And when we look at DNA, there's a phosphate backbone that creates that double helix structure. And those base pairs, so the base pairs keep the structure together, and the phosphate backbone actually creates the shape of the molecule that sort of rotates like a double helix. And those long chains of these almost create like a set of like bits in a computer. Like, do you guys know that computers store information in bits, like ones and zeros? It's the same case here. DNA is storing this in ones and zeros, except it's storing it in like an AT pair would look like AT, or an adenine thymine pair would look like a AT, and a guanine cytosine pair would look like a GC. So it goes like AG, GA, all that stuff, and that essentially creates these long sets of bits that are almost like computer code. So the big takeaway is that these are held together. Those phosphate backbones. Do you guys see that those phosphate backbones are polar? Or rather, they're not polar, but no, they are polar. Those phosphate backbones are polar because that oxygen is negative, and that phosphate is attracted to that negative oxygen on that phosphate backbone. I'm looking at the very top left in that DNA molecule. Yeah, so it creates that backbone for the DNA, and that creates the shape of it. Whereas the base pairs actually keep the structure together from falling, or keeps it from falling apart. Does that make sense? Yeah. So the big chemistry takeaway here is that like you can draw a lot of conclusions about like, the shapes of molecules and how they, or not how they function. You can't really talk about how they function just by the bonds between them or the forces between them. But you can really really a lot of this stuff starts making sense when you think about the intermolecular forces between them. And like for example, it's definitely fair for you to be given like that DNA structure on the left, or minus like the organic notation because it has those carbons emitted in the skeleton structures. But it's definitely fair for you to be given that that structure and asked for you to like talk about like the hydrogen bonds in them. So next one is heme B. So again, this is organic notation. There's carbons wherever there's an unlabeled elbow, and each unlabeled elbow should have 4 bonds to it. So if there's not 4 bonds to it, then the rest of the bonds are taken up by hydrogens that are emitted from the page. So the theme here, or rather heme B, every species hemoglobin is made up of 4 different hemes, or 4 different types of hemes. And this is heme B. This is a type of heme that makes up hemoglobin in humans. So 4 hemes make up hemoglobin, and then 4 depend on species and age too. Actually, infants have different hemes in their hemoglobin than adults do. So the theme here is biomolecules tend to have hydrogen bonding because it's very efficient and very strong. Like if you think about like structural integrity, there's only really 3 ingredients in the structural integrity of molecules bounded by hydrogen bonds, right? There's just hydrogen, a nitrogen, oxygen, fluorine, and then a separate nitrogen, oxygen, fluorine. And that's crazy effective for keeping strength and integrity in a set of molecules. So that's the theme here. Does that make sense? I hope the heme and the DNA are enough of an example to talk about like hydrogen or biomolecules tend to have hydrogen bonding. Does that make sense? Okay, cool. So there's other biomolecules. There's RNA, there's lipids, there's monosaccharides, there's metabolites, etc. And these all fulfill a special role in the body depending on the structure, and especially the IMFs with the molecules around it. Especially all that. So I have a big structure coming up that I'm going to try and pronounce. If I get it wrong, feel free to make fun of me. So the following molecule, phosphatidylcholine, or PC, is a dominant component in the cell membrane. What is the strongest type of IMF present in a sample of this molecule? So go ahead and look at that. When you see a CH2, that means a C, but there's 2 hydrogens coming off of the carbon. I just didn't want to draw that hydrogen. So what do you guys think the strongest type of IMF present in the molecule is? You'd think so, but it's not. So we're gonna go to the drawing board and talk about this because it's a little weird. So the criteria of hydrogen bonding is 3 of the molecules in there is a nitrogen, oxygen, and a fluorine. So there's only really one. There's only a few places where it could ever occur. It would be right here, right here, right here, right here, 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 and here. And the other set of criteria is that there's a hydrogen bond with either an oxygen, a fluorine, or a nitrogen. Are any of those blue circled atoms on the molecule bonded with the hydrogen? Right. So the criteria for hydrogen bonding is not met. But this is polar because those nitrogen chlorine bonds are polar in the bottom left. Actually, no, this total thing does not contribute to the polarity, but definitely this, definitely this, definitely this, and this all contribute to the polarity of the molecule. This may, I'm not sure, but because I don't know the geometry around that phosphorus. So there's dipole-dipole attractions in this molecule, but there are not hydrogen bonds. Does that make sense? Yeah. So I'd say when we're looking at molecules, step one is when we're looking at the forces between them, look for FON. Look for a fluorine, an oxygen, or a nitrogen. So there's two steps here, or there's like a tree diagram here. There's two things here. What's the case if there's none of these? So the next step, if there's none of these, would be look for other polar bonds. We'll call it PB. And then what's the case? That branch of the tree is no. So what's the case if there aren't any other polar bonds in the molecule? Go ahead and shout it out in the chat. What would be the strongest force in a molecule if there are no polar bonds in the molecule? IMS. I think you're confusing the abbreviations. It would be LDFs. So no, there'd be LDFs. And if there are other ones, it would be dipole-dipole. Now look, so if there's FON, the next step when you're looking at these is look for the bonds between hydrogen and fluorine, hydrogen and nitrogen, or hydrogen and oxygen. So what's the case if there's not any of these? If there are FONs, but there's no HF, HN or HF. Yeah, dipole-dipole. So this goes here. And if there are HF, then it's H bonding. So that's pretty much that tree diagram summary there, the entire stream. One thing that I did not mention is LDFs are also sometimes called van der Waals forces. I'm not sure why. My guess would be that two different guys discovered the same thing, or two different guys or scientists, they could be women, I don't know, discovered the same thing at different times independently, so they both got credit for it. Maybe one of them was a physicist and one was a chemist, and both communities wanted to talk about or take credit for it. So that's it, really, for all that, actually. Yeah, I mean, that's really that's all the content. So does anyone have any questions in general that I can answer about any of the material? Awesome. So if you do have a question about homework or just a chemistry concept in general, I did put my Instagram in the chat. Yeah, I'll put the last slide. Yeah, I'll put I don't think you're talking about the slide, but I think you're talking about the application window that I was talking about. Were you talking about that? Yeah. So if you have a question about chemistry, you talk about study tips with me, really anything. That's my Instagram in the chat. Feel free to shoot me a DM. But yeah. Anything else besides wanting that tree diagram back up? And of course, there are like some exceptions to that tree diagram, like if there could be FON in the molecule without there being a net dipole moment in the molecule. I think NH4 would be an example of that. But yeah, really the best advice I can provide is draw out the structure and analyze it that way. But if you're stuck on the structure, just look at the FON or use that tree. So last call for anything last minute? All right, what's up, Amelia? I'm not going to shut the stream off on you. Best way to study for FRQs? Just do them. Like College Board releases the FRQs for every year on their website. I think it's truncated to like 2013 because the exam changed then, but you can certainly find certainly find stuff on for previous years. But yeah, really the best thing would be just to do them, do the previous ones in the past. One thing I will say is it's very important for an FRQ that you really show your entire thought process. Because it's very rare that someone will get a perfect score on an entire FRQ. It's very common that someone gets a perfect score on an FRQ just because they showed all their work and all their work led to some partial credit because there was some correct thinking in their thought process and you get some credit for that. On this exam, it's really not, do you know chemistry perfectly? It's, do you sort of know chemistry? Because really, no high school student's going to really know chemistry well. Like, you can have a high school student that knows, like, history perfectly, that knows all the... Awesome, cool. Have a good night. I'm going to keep on talking about the FRQ thing. But yeah, good night. So that'd be awesome if you would share this this resource, because I love having viewers. But yeah, I mean, really a big thing is just show your work. Like, people, the most common mistake or the most crucial mistake that really I see people making is they don't show any work. They just put down a number and the number's wrong. But really, like in a history class, like the answer, someone can know American history from 1920 to 1948 perfectly, but just being a high school student that studied a lot, but you won't, no one will get chemistry perfectly. So the whole point there is your thought process in the right direction. And you should really be showing that your thought process is in the right direction to get the most credit possible. Yeah, like I had a guy sit next to me. I actually think he was cheating off me like all year. But I had a guy sit next to me that would just constantly get FRQs wrong because he was just putting down an answer. And whether that was because he was copying me or because he just didn't understand the material, either way, he was screwing himself over because he wasn't doing the work. Yeah, but I mean, that's really the best tip I can give you. And also the best thing is to, like, if you see a number, make sure that number makes sense. And like try and operate within the domain of the question. Like, don't extend a question that asks you about polarity to molecular geometry too much. It does help, but if you can't, don't worry about it. And yeah, I can't link College Board's FRQ stuff because this is not technically an educational institution like a university is. This is a private corporation, so I can't use copyrighted material. But you can definitely look up College Board AP Chem FRQs and just practice. There's also resources online where you can find some of those unreleased FRQs, but if you get caught doing that, you might get in trouble because those are not allowed. So I'm not telling you to do that, but if you really need the practice, they're not too hard to find. So yeah, if that's it, then yeah, sure thing. I'm gonna go ahead and end the stream if that's it. Have a good night. Take it easy. There it is. Night, guys.